Hey there, Keys Precalculus. Welcome to the last section of 2.3C, where we are going to review some tools that will help us find all the zeros of a polynomial function. The tools we're going to look at today are the rational zero test, we're going to look at Descartes' rule of signs, and we're going to look at the upper and lower bound rules. Some of this is review, some of this may be new to you, but these are tools to help you figure out what the zeros of a polynomial are more easily. The first test we're going to look at is the rational zero test. This is in your book on page 118, but I went ahead and rewrote it up here with colors. The rational zero test says that if a polynomial f of x, which I listed, has integer coefficients, then every rational zero of f has the form p over q, where p and q have no common factors other than 1. In other words, it's a fraction that's reduced. P is a factor of the term a sub 0, which is the constant, and q is a factor of the leading coefficient a sub n. In other words, if this polynomial has rational zeros, then those rational zeros will come from the list of the factors of a constant term divided by the factors of the leading coefficient. Remember, a rational number is a ratio, and a ratio is a fraction. If a number can be written as a fraction, it is a ratio. Now, irrational numbers are square roots, cube roots, roots that have no perfect root, or non-repeating, non-terminating decimals such as pi or e. But rational numbers can be written as fractions, and if you can find if a polynomial has a rational zero, then it will be in the form of the constant divided by the leading coefficient. You've done this before in algebra. We're going to do it again right now with an example. So let's look at this polynomial. F of x equals x to the third plus x plus 2. If I tell you to find all of the rational zeros, you say, where do I start? How do I start figuring out which ones would be zeros? Do I just test every rational number I know? No, let's narrow it down. We can narrow it down. We know by the rational zero test that if this polynomial has rational zeros, they will be of the form p over q, where p is a factor of the constant, and q is a factor of the leading coefficient. In this case, the leading coefficient, we don't see it, it's a 1. Okay, so I need to find out all the possible rational zeros. So the first thing I'm going to do is I'm going to list all of my factors of the p. So all my possible factors of p are positive and negative 1 and positive and negative 2. Now I'm going to list all my possible factors of q, or all of the factors of q. That's the leading coefficient, and that's just positive and negative 1. Now I'm going to write them in the form of p over q. And in this case, because q is 1 and that the denominator of 1 is understood, we don't have to show it, all of my possible rational zeros are going to come from this list of p right here. Okay? So now I need to test them. And I can test them by substituting them in, finding f of x, or f of positive 1, f of negative 1, f of positive 2, f of negative 2. I can plug them in, or if it's a long polynomial, I would use synthetic division. I think it's easy just to plug them in and evaluate, so we're going to do that now. So I'm going to start with f of 1. If I plug in 1 into x cubed, 1 is 1 cubed, it's right here, 1 cubed plus 1 plus 2. Does that equal 0? No, that equals 4. So it is not a rational zero. Now I'm going to test f of negative 1. I get negative 1 cubed plus negative 1 plus 2. This becomes negative 1 minus 1 plus 2. Yes, that equals 0. Therefore, a negative 1 is a rational zero of this function. I'm going to go ahead and test the other two because I did not do synthetic division. But then I'll show you another way to do this with synthetic division so you don't have to test everything. Okay, so f of 2 would be 2 to the third plus 2 plus 2, which equals 8, plus 2 is 10, plus 2 is 12. That does not work. And then f of negative 2 is negative 2 to the third, which is negative 8, plus negative 2, which gives me negative 10, plus 2, which gives me negative 8. That does not work either. So the only rational zero of this function is the number negative 1. In other words, x equals negative 1, or if you write it as an ordered pair, because it's a 0, it's the point negative 1, 0. Okay, now I'm going to show you this with synthetic division. So I'm going to test my points in the numbers 1, 0, to hold the x squared place value, 1, and 2. And I'm going to see if they leave me a 0 here or a different remainder. Okay, we know that 1 didn't work, but I'm going to go ahead and test it anyway to show you. 1, bring down the 1, 1 times 1 is 1, 0 plus 1 is 1, 1 times 1 is 1, 1 plus 1 is 2, 1 times 2 is 2, 2 plus 2 is 4. That does not work. Okay, but I could test negative 1 instead. The next one, 1, 0, 1, 2. I guess I should mark through the whole thing here so we know that that doesn't work. Okay, let's see if my remainder is 0. Bring down the 1. Negative 1 times 1 is negative 1. Negative 1. Negative 1 times negative 1 is positive 1. 1 plus 1 is 2. Negative 1 times 2 is negative 2. And negative 2 plus 2 is 0. So yes, I know that this is a rational zero. So I know that x to the third plus x plus 2 can be factored into x plus 1, remember I have to change the sign, times, now I'm going to use these as the coefficients, x squared minus x plus 2. Now, can x squared minus x plus 2 be factored into rational numbers? Can I do it by grouping, or can I do it with, by grouping? No, I can't. There are no two numbers that I can multiply together to get negative 2, or positive 2, sorry, and add to get negative 1. 2 times 1 gives me positive 2, but when I add them I get 3. Negative 2 times negative 1 also gives me positive 2, but when I add them I get a negative 3. So there's no rational numbers that I can factor this into. I would have to use the quadratic formula, and when I did that, I would see that I would have no other real roots. So the only real root, which is a rational root, of this function is negative 1. And I found that I narrowed my choices by using the rational zero test. Now let's do another one. Let's find all of the rational roots of f of x equals 2x to the third plus 3x squared minus 8x plus 3. So the first thing I'm going to do is I'm going to find my factors of p right here. Find the factors of the constant term, which are going to be plus, positive and negative 1, and positive and negative 3. Now I'm going to find the factors of my leading coefficient. The leading coefficient is 2. That's q. So that's going to be positive negative 1 and positive negative 2. And now I need to list all of my possible rational zeros in the form of p divided by q. Okay, so what I'm going to do here is list all of my possibilities. I'm not going to use colors because it's going to take too long to switch over back and forth. I am also going to try to switch, or excuse me, I'm going to try to go in order as systematically as possible. Now all of my rational zeros are going to be in the form of positive and negative. I don't want to rewrite one number and then write it again as a negative, so I'm going to write everything with a plus minus. And I'm going to start with the first blue one, the 1, and I'm going to put it over every red one. So I'm going to say 1 divided by 1 is 1. It gives me a positive and negative 1. That's one possibility. Then I'm going to also try 1 over 2. So I've taken my first blue one and I put it over the second red one. So possible answers are positive, negative 1, positive, negative 2. Now I'm going to do it with the 3. Positive, negative 3 over 1 is just going to give me positive or negative 3. And now I'm going to put the 3 over the 2. So positive, negative 3 over 2 is positive, negative 3 halves. So here I have 1, 2, 3, 4, 5, 6, 7, 8 possible rational zeros. There won't be 8. There can be at most 3. But if it has any, it will come from this list of positive, negative 1, positive, negative 1 half, positive, negative 3, or positive, negative 3 halves. That's a fairly significant list, and it can get even longer if my leading coefficient and or my constant have many factors. So it's easy to narrow this down if I graph it first to get a general idea of where one of them might be. So we're going to go over to Desmos and look at the graph of this polynomial. So when I come over here to Desmos and I graph it, I don't know if you can see my cursor or not, but I see that this is a graph who looks like it crosses the x-axis at a 1, a negative 1 half, and maybe a negative 1, 2, negative 3. So I can test any of these. I can test my 1 half. I can test my 3. It might not be 1 half. It might be 2/3. I don't know, because it crosses somewhere here in the middle. But it also looks like it crosses at 1, and it looks like it crosses here at negative 3. So I think I'm going to choose one of those to test first. So let's go back over to our polynomial and test them. So let's go ahead and test the 1. Okay, so I'm going to put the 1 up here outside my synthetic division box. And I'm going to put my coefficients 2, 3. I do not need any placeholders in this one. Negative 8 and 3. And let's see if 1 works. Drop down the 2. 1 times 2 is 2. 3 plus 2 is 5. 1 times 5 is 5. Negative 8 plus 5 is negative 3. 1 times negative 3 is negative 3. So my remainder is 0. So yes, 1 is a rational zero. Therefore, x minus 1 is a factor. Now I'm going to look at I'm going to take my my quotient, and I'm going to use these as coefficients for my new polynomial. 2, x to the, I go 1 degree less than the 3, so x squared, plus 5x minus 3. Now, can this be factored? Can it be factored by grouping? Yes, it can. I say, what two numbers can I multiply to give me the leading coefficient times the constant, which is negative 6, and add to give me my middle term, which is 5. Well, I can multiply 2 times 3, negative 2 times 3, and that would give me negative 6, but that won't add to give me a positive 5. And if I say positive 3 times negative 2, that still won't give me my adding to be positive 5. But I could do negative 6 times 1. That won't give me a positive 5. Negative 6 times 1 is negative 6, but adding together gives me a negative 5. So what I need to do is multiply a positive 6 times a negative 1. So over here, when I factor by grouping, I'm going to rewrite this as 2x squared minus, and I'll say plus 6x minus 1x minus 3. Now, when I do this, I'm going to change my color here so you can see it better. I'm going to group, color's not wanting to change, hang on, there we go. I'm going to group these two together, and I'm going to make this plus a negative right here, and I'm going to group these two together. So I'm making my 1 a negative. I don't know if you can see it very clearly, but I have. Now, the factors, I'm going to ignore this for now. We'll bring it down later. my factors of 2x squared and 6x, my common factors are 2x. So I can factor that out, and I'm left with an x plus 3, because if I were to distribute the 2x back into here, 2x times x gives me 2x squared, 2x times 3 gives me 6x, plus the factors, the common factors of negative 1x and negative 3, I'm going to take out a negative 1 and be left with x plus 3, because I want this to be the same as that. Okay, so when I finish factoring this, I'm going to end up with 2x minus 1 times x plus 3. So this business here that I'm putting a box around factors into that. Now I can also multiply it by this x minus 1. So now I have my 3 factors, which I can find my 3 rational zeros. We already knew that one of my rational zeros is 1. Here, with this one, it's going to be negative 3. And with this one, it's going to be positive 1/2. So the graph was right. We saw it on the graph. So my rational zeros are x equals, if I do it in ascending order, negative 3, 1/2, and 1. And that's how you use the rational zero test to narrow down your choices when you're looking for the rational zeros of a polynomial. You should go ahead and work through example 9 on page 120 in your book. Try to work through it on your own, then check it with the work that they have in the book just for more practice with this. But there are also some other tools that you can help narrow your choices down even further. And the next tool we're going to look at is Descartes' rule of signs. If we let f of x be our polynomial with real coefficients, it doesn't have to be rational or integer, it just has to be real coefficients, and your constant term is not 0, then the number of positive real zeros of f, we're not talking about rational, we're just talking about real zeros. The number of positive real zeros of your function is either equal to the number of variations of sign of f of x or less than that number by an even integer. So we just reduce it by 2. So let's say there were 5 changes, then you could have 5 or 3 or 1 positive real zeros. If the number of negative real zeros of f, if you have this polynomial under these conditions, then the number of negative real zeros of the function is either equal to the number of variations of sign of f of negative x or less than that number by an even integer. I believe you did this in Algebra 2. We're going to look at one example to see how this works. So let's look at this polynomial, 3x to the third minus 5x squared plus 6x minus 4. And let's see if we can find all the, describe all the possible real zeros of this function. Find out how many are positive and how many are negative if we have real zeros. So the way I'm going to do it first is I'm going to look for the positive. And I'm going to look for the variation in sign. And what I mean by variation in sign is when you've got 2 terms next to each other, when they're written in descending order, you do not have to have placeholders. You don't have to have every variable or exponent represented. But if you write them in descending order with the proper signs, the 2 that are next to each other, if they have different signs, that's a variation in sign. So positive 3 to negative 5 is a variation in sign. So there's one variation. And then I go from negative to positive again, that's a second variation. And then I go from positive to negative again, that's a third variation. So there are 3 positive variations. So I can have, for my positives, I can have 3 positives, or I can have 3 minus 2 positives, which is 1, and that's it. So I'm going to have either 3 positive real zeros or 1 positive real zero. Now I'm going to look at it with the negative. I rewrote my equation here with a negative x in place of every x. So when I simplify this, f of negative x is equivalent to negative x to the third power gives me, it changes this sign. Basically, I'm going to change my sign every time I have an odd power. Negative x squared becomes positive x squared, so it does not change that sign. It stays a negative 5x squared. 6 times negative x is negative 6x. That was an odd power. It changed the sign, minus 4. So now I'm going to go over here and count my variations in sign. There's no variation between the first term and the second term. There's none between the second and the third. And there's none between the third and the fourth. So there are 0 negative variations. So my negative reals, I have none. Now this number 3, 1, and 0 are not the zeros. They're the number of possible zeros. So I can have either 3 or 1 positive real zero for this equation, or I can have no negative real zeros. So I use this information to narrow my choices. Or I should say, I use this information along with the rational zero test to narrow my choices. So let's go ahead and do that. Let's look at my p's and q's and see what my possible rational zeros are. So my p's are the factors of 4, which are positive negative 1, positive negative 2, and positive negative 4. And my q's are the factors of 3, which are positive negative 1 and positive negative 3. But I know I can knock out all of my negatives because by the Descartes rule of signs, I will have 0 negative roots or zeros. So I don't have to write my negatives anymore. So my p over q's are going to be 1, 1/3, 2, 2/3, or 4, or 4/3. So instead of having 12 choices, I have 6 choices now. So I've narrowed it down. And if I come over here to Desmos and I graph it, I see that it only crosses the x-axis at one point, and it looks like it's the point 1, 0. So that really narrows my choices down. So I can come back over to the equation, or rather I can come back over here to the polynomial, and I'm going to go ahead and test my 1 algebraically by using synthetic division just to make sure that it's a 0. So I'm going to list my coefficients as 3, negative 5, positive 6, and negative 4. I don't need any placeholders. Bring down my 3. 1 times 3 is 3. Negative 5 plus 3 is negative 2. 1 times negative 2 is negative 2. 6 minus 2 is 4. 1 times 4 is 4. 4 minus 4 is 0. Therefore, I see my remainder 0. So one of my positive roots is 1. Now, by looking at the graph, I saw that there was only 1. That means it only crosses at one time. And I can further find this by saying x. Here's one of my factors, x minus 1, because 1 is a root. And my other factor is 3x squared minus 2x plus 4. Now, when I try to factor this, I see that it cannot be factored. So I would use the quadratic formula. But before I do that, I would look and see what my discriminant is. My discriminant would be negative b, it's b squared, which is 4, minus 4 times a times c. Well, 4 minus a number bigger than that is going to be a negative number, so that gives me no real solutions. So I know that my other two solutions are not real numbers, and I could see that by the graph because it only crosses the x-axis one time. Therefore, these are my two factors, x minus 1 times 3x squared plus 2x plus 4, and my only real zero is the point 1, 0. So we see how Descartes' rule of signs helped us narrow down our choices. We can test to see how many positive reals there are and how many negative reals there are, and it narrows down my choices. There's one more test we're going to look at, and that test is for the upper and lower bound rules. It's an extra test. It just helps narrow your choices. It says, let f of x be a polynomial with real coefficients and a positive leading coefficient. So we can have any real coefficients, but our leading coefficient has got to be positive. Then suppose f of x is divided by x minus c using synthetic division. In other words, we're going to test one of our possible rational zeros by plugging in c into synthetic division and seeing if it's 0. But it doesn't matter if it is or isn't. If the number c is greater than 0, so the number that we test is greater than 0, is positive, and each number in the last row of our synthetic division is either positive or 0, then c, that number c, is an upper bound for the real zeros of f. That means that I will have no number greater than that number c as a 0. But if I'm testing c and it's a negative number, so it would be x plus c in other words, if c is less than 0 or negative, and the numbers in the last row of my synthetic division are alternatively positive and negative, and 0 entries count as positive and negative, so they would be an alternate, then c is a lower bound for the real zeros of f. That means that c would be the smallest number, that rational number that I could find, or any number that I could find as a 0 of the polynomial. So let's go ahead and do one more problem that illustrates all three of these: the rational zero test, the Descartes rule of sign, and the upper and lower bound rules, just so you can see how it all works together to make your job simpler to find the zeros of a polynomial. So in example 11, our problem states, find all the real zeros of f of x equals 6x to the third minus 4x squared plus 3x minus 2. So we're going to start with doing the rational zero test. I'm going to list my p's, which is the factors of my constant, which is going to be factors of -2, which are positive -1 and positive and -2. And then I'm going to list my q's, which are factors of the leading coefficient, which are positive and -1, positive -2, positive -3, and positive -6. So my p over q's are going to be positive -1, positive -1/2, positive -1/3, and positive -1/6. My goodness. Then I've got to list the 2's. Positive -2. Positive -2 over 2, it reduces to 1, so that's reduced. Positive -2/3, and then positive -2 over 6 reduces to positive -1/3. So I've got 1, 2, 3, 4, 5, 6. I have 12 choices to test synthetic division to see if I have any of these are rational real zeros. So if any of my zeros are rational, then they would be among that list. But before I do that, I'm going to do my my Descartes rule of signs. I did not mean to draw that synthetic division box there. I'm going to do Descartes rule of signs to see if I have any, if I can narrow my choices from the positive to the negative. So here, between +1 and -4, there's a sign change. And then -4 to 3 is a sign change, and +3 to -2 is a sign change. So my positive sign changes are 3, so I can have 3 or 1 positive answers. Now I'm going to do f of negative x here, and if I plug in a negative x for 3, for the x to the third power, I know I changed my sign, because remember I changed the sign for every odd power. So that changes. -4x squared does not change. 3x changes to -3x and -2. So I look here and I see that there are no sign changes between the first and the second term. That's not a sign change. Between the second and third term, that's not a sign change. And between the third and the fourth, there's not a sign change. So my negative sign changes are 0. I will have 0 negative answers. So I have just narrowed my choices, my rational choices, down from 12 to 6. I could graph it if I want, but I'm not going to this time. I'm just going to test because I want to show you how the upper and lower bound test works. Okay, so I'm going to come over here and I'm going to test the first one. I'm going to test positive 1 into synthetic division. And I'm going to put in 6, negative 4. These are the coefficients of my polynomial. I don't need any placeholders. 3 and negative 2. So I'm going to go ahead and bring down my 6. 1 times 6 is 6. 6 plus negative 4 is 2. 1 times 2 is 2. 3 plus 2 is 5. And 1 times 5 is 5. Negative 2 plus 5 is 3. This is not a 0. 1 is not a 0. However, because my leading coefficient is positive right here, and the C that I tested is greater than 0, I can come up to this rule that says if C is greater than 0, and each number in the last row is either positive or 0, C is an upper bound. Well, look at this. My C is positive because I'm testing x minus 1, which means that I'm testing a positive 1, and that's greater than 0, sorry. And each one of these is either positive or 0. That tells me that the number 1 is an upper bound. That means I am not going to have any zeros that are bigger than 1 in my polynomial. That means that knocks out 2. So that knocks out the number 2. So I know that I don't even want to bother testing 2. I have to test everything that is positive that's less than 1. So I can test 1/2, 1/3, 1/6, and 2/3. Those are the fractions that I could test to see if one of them is a real 0. For the sake of time, I'm not going to test all of them. I'm just going to go to the one that I know works. You would, on your homework, you would be testing, or you could look at a graph and to narrow your choices. But I'm going to test 2/3. So 6, negative 4, 3, and negative 2. I'm going to test that with synthetic division here. Bring down my 6. 2/3 of 6 is 4. Negative 4 plus 4 is 0. 0 times 2/3 is 0. Bring down my 3, because 3 plus 0 is 3. 2/3 of 3, the 3's cancel each other out, is left with 2, and negative 2 plus 2 is 0. So I see that 2/3 is a 0. Therefore, x minus 2/3 is a factor, and the other factor is going to be 6x squared plus 0x plus 3 equals my f of x. Okay, so those are my two factors. Now, if I were to see what the real 0 of if there's real zeros other than 2/3, then I would say x minus 2/3 times 6x squared plus 3 equals 0. And so I could set each one of these, which I already know that x is 2/3, equal to 0. So I'm going to set my 6x squared plus 3 equal to 0. And if I take my 3 and move it to the other side and divide by 6, then I get x squared equals negative 1/2. Well, I know I can't take the square root of a negative number and get a real answer. So there are no more real zeros. The only real 0 for this polynomial is the number 2/3 right here. Okay, so that's how you use all of the tests, all of the tools to narrow your choices to find all the real zeros of a polynomial. All of the polynomials that we have dealt with in all of these videos have had a power of 2 or 3. If you were to have a power of 4 in your polynomial, then you would do the same thing, but you would perform synthetic division twice. You would perform it once to narrow your factors down to a binomial times a polynomial with the power of 3. Then you would do it again with the new coefficients to go down to a polynomial with the power of 2. So x to the 3. Then once we get to a power of 2, which is a quadratic, you can either find its factors, if it has real factors, by factoring it, by completing the square, or by using the quadratic formula. And the quadratic formula will give you all of the factors, whether they're real or not. So you just keep doing this process over and over till you narrow it down to a quadratic. Okay, I hope this helps with your homework. Have a great weekend.